AP Chemistry, we are moving into Unit 2, unit called Reactions. So up until now we've talked about individual atoms and how atoms join together to form chemical compounds. Now we're going to start talking about how compounds react with one another to form other compounds, and this is really the heart of chemistry. And these are going to be expressed through chemical reactions and chemical equations. So we need to understand the concept of a mole. So a mole is that very large number of anything. Just like a dozen represents 12, whether it's 12 donuts or 12 eggs or 12 of anything, a mole represents that number of anything. Now in this class, of course, we're talking about the anythings are going to be atoms, molecules, ions, electrons, things on the atomic and molecular level. So this number is called Avogadro's number. And in scientific notation, a mole is written 6.022 times 10 to the 23rd. So remember, you can think of an atomic mass unit as the mass of a single proton or the mass of a single neutron. That's just basically the definition of an atomic mass unit. Here's the problem. We can't measure the mass of a proton, neutron, atom, or molecule on a scale. They're too small for us to see with our eyes. They're too light for us to be able to weigh on a scale. So what do we do? An oxygen atom has a mass of 16 atomic mass units. That means it has 8 protons and 8 neutrons in the most common isotope of oxygen. But we can't measure 16 atomic mass units on any kind of a scale. We measure mass in grams. That's the standard unit for mass in the world. And you felt what a gram was when you felt those little blue blocks in class. So we need to get things in the scale of grams. And one atom, one molecule is nowhere near 1 gram. So we need to scale this up. So we measure mass in grams and we have scales for that. So here's one oxygen atom. It's 16 atomic mass units. What if we knew how many oxygen atoms it would take to have a mass of 16 grams? Then by knowing the number of grams of oxygen, we would know how many oxygen atoms we have. In other words, the key to that is you have the number 16 AMU, and you want to convert it into the same number value, 16, but in the unit of mass that we can measure in the laboratory, which is grams. And what they found is there's a standard number of atoms or molecules of any substance, but in this case of oxygen, that will get you from 16 AMU to 16 grams. So then the question is, how many atoms? How many is that? Well, the answer is Avogadro's number. 6.022 times 10 to the 23rd is the number of atoms that will convert the mass of a single atom, oxygen atom, 16 AMU, to the same number of grams, 16 grams. So that's the only number that's true of. It's exactly 16 atomic mass units times 6.022 times 10 to the 23rd will give you exactly the same numeric value, but in grams, 16 grams. And there it is. And that's going to be true of any atom or any compound that we deal with. To go from AMU, which is on the atomic or molecular scale, which we can't measure, we can't see, up to a number that we can measure, we can see, grams, we want to multiply by that number, Avogadro's number, which we call, in practice, we call it a mole, M-O-L-E. So this is the atomic mass of a single oxygen atom, and this is the molar mass of a mole of oxygen atoms, and it's 16 grams. So get used to that word molar mass. It's the mass of 1 mole of a substance, and you're going to hear that word every day. So be clear on what it is. It's the mass of 6.022 times 10 to the 23rd, whatever you're dealing with. And if it's more than 1 mole, then it's going to be more than 16 grams. For example, 2 moles of oxygen would be 2 times 16 grams, would be 32 grams. So we'll talk about those conversions in just a moment. So the relationship is true for any element or compound by taking the atomic mass in AMU and multiplying by Avogadro's number. You can get the molar mass. So we're going to start with carbon. Carbon, the average carbon atom, the average of all the carbon isotopes is 12.01 atomic mass units. So just think of that as the mass of a single carbon atom. If you multiply that by a mole, you get the same number, but it's in grams, 12.01 grams. Nitrogen. You get these numbers off the periodic table. They're down at the bottom of each element. So nitrogen, you're going to see on your periodic table is 1401 atomic mass units for a single nitrogen atom. If you multiply that by a mole of nitrogen atoms, then you're going to have the molar mass of 14.01 grams. Neon. Look at your periodic table. Down below the Ne, you see 20.18 atomic mass units. Multiply that by a mole of atoms of neon, and you get 20.18 grams of neon per mole. So the molar mass of neon is 20.18 grams. Aluminum, 26.98 atomic mass units. You multiply that by a mole of aluminum atoms, and you get 20.98 grams for the molar mass. Sulfur, off your periodic table, 32.07 atomic mass units for a single sulfur atom. You multiply that by a mole of sulfur atoms, and you're going to end up with 30.07 grams. So 6.022 times 10 to the 23rd is the only number that will do that. We'll take the number of atomic mass units, which is what we measure individual atoms or molecules in, and scale it up to the same exact number, numeric value, but in grams, which is a number, which is what we have, which is what we work with in the lab. That's what our scales measure. They measure things in grams. Here are some common examples of chemical molecules and compounds. So H2. So hydrogen, as we talked about in the foundations unit, that hydrogen doesn't exist just as atoms in gas form. They like to pair up and form H2 molecule. That's 2 hydrogen atoms put together. So 2 hydrogen atoms bonded to form 1 hydrogen molecule. That's H2. So the way you write that is the 2 atoms are shown as a subscript right there. H2O. You have 1 oxygen atom and 2 hydrogen atoms, and that forms a molecule. H2O is also a compound because it's 2 or more elements. H2 is not a compound because it's just a single element. CO2 is 1 carbon and 2 oxygen atoms, and that forms both a compound and a molecule. Again, they're molecules because they're covalently bonded. All 3 of these are covalently bonded. They're non-metal. The strong guy, they share electrons, so they form molecules. Those are individual structures that can separate from each other. NaCl, that's 1 sodium and 1 chlorine atom. Now that's an ionic bond. It's a metal, the Na, a weak guy, and the chlorine, a non-metal, a strong guy. The chlorine takes the electron away from the sodium, becomes negatively charged, the sodium becomes positively charged, and they stick together. So that's not technically a molecule, but very loosely people would call that a molecular formula for sodium chloride, even though NaCl is a formula unit. Remember, you won't find an NaCl all by itself the way you might a CO2 or an H2O. You'll find it in a brick wall structure with a lot of other NAs and Cls. There just happens to be 1 Na for every Cl. It's a 1-to-1. But they're basically like apartments in an apartment building. You can tell one from the other, but they can't be separated. But still, it's sometimes we refer to NaCl as being a molecule or a molecular formula for sodium chloride. O2, 2 oxygen atoms bonded to form an oxygen molecule. Again, not a compound, but it is a molecule. Covalently bonded. The small number after atoms is called a subscript. A subscript of 1 is not written. So in CO2, carbon, there's 1 carbon, but you don't write C1O2. It's just CO2. H2 and O2 are covalent bonds that form molecules. They are not compounds because they have only one element. If a number appears in front of a chemical formula, it means that there is more than one molecule or formula unit of that formula. So 2H2O means that there are two H2O molecules. So in all, you have a total of 4 hydrogen atoms. So 2 times 2, you kind of distribute that coefficient 2 through the entire molecule. So you have 2H2. That means you have 4 hydrogen atoms in all, and you have 2 oxygens. So again, it's like a distribution. 2 times the H2 and 2 times the O. 3CO2 means that there are 3 carbon dioxide molecules. That means you have 3 carbon atoms and a total of 6 oxygen atoms. 4O2 means you have 4 oxygen molecules, and there are 8 oxygen atoms in 4 oxygen molecules. Each molecule has 2 oxygen atoms. The large number in front is called a coefficient, just like in algebra class. It indicates how many of the complete units you have. The atomic mass of a molecule or unit cell is computed by adding the atomic masses of each atom times the number of atoms. In moles, this is the same number, but it's measured in grams. So let's take a look at water. So the atomic mass of a single water molecule, there you have it. You have 2 hydrogens. Each one is 1.01 atomic mass units, each atom. And then oxygen is 16 atomic mass units. And you get those from the periodic table, those numbers. So you should look at your periodic table and confirm that you understand where those numbers came from. If you add those up, 2 hydrogens plus an oxygen, you get 18.02 atomic mass units for a single water molecule. Now the molar mass of 1 mole of water molecules is exactly the same numbers, except now you're dealing with 6.022 times 10 to the 23rd molecules. So the only thing that changes is the unit of measure becomes grams. So if you look at that there, all the numbers are the same, but the units of measure is grams. So the mass of a mole of H2O molecules, of water molecules, is 18.02 grams. So numerically the same. It's just now you're working in a unit of measure of mass in grams that we can measure in a laboratory with a scale. Here's one more example. So for more than 1 mole, you can count the number of moles of each type. So here we have 2 CH4. That means you're going to have 2 carbon atoms. Each one is 12.01 grams, so we're talking molar mass now. We're going to skip over AMUs, go straight to molar mass. So that's 12.01 grams. You get that from your periodic table. And then you have each methane molecule has 4 hydrogen atoms, and you have 2 methane molecules. So that's a total of 8 hydrogen atoms. So it's 8 times 1.01. And when you add all that up, the mass of 2 moles of CH4 is going to be 32.10 grams. Again, working backwards, turning that around, what that means is if you measured on a scale and you knew you had methane and you knew you had 32.10 grams, then you would know exactly how many methane molecules you have. You have 2 moles, or 2 times 6.02, 2 times 10 to the 23rd molecules of methane. So you work backwards from how many grams do you have and knowing the substance to how many atoms or molecules you have. So these numbers are the atomic mass numbers from the periodic table, but now we're going to call them molar mass because we're talking about a mole of CH4 molecules. We now think of them as molar mass. So here's a table I'm going to have you work through a few of these. So complete the table below and answer the questions. So we're going to take water, H2O, there's the hydrogen, there's the oxygen, and then there's the compound H2O. So the number of atoms or molecules, in the case of hydrogen we're talking about atoms, there's 2. Oxygen, there's 1. And 2 and 1 gives you 1 water molecule. Don't add up the 2 and the 1 to get 3. Think of it like a bicycle. To make a bicycle, you need one seat and two wheels to make one bicycle. So to make a water molecule, you need one oxygen and two hydrogen to make one water molecule. So don't add up those numbers. The atomic mass, again, we get it off the periodic table. It's 2 times 1.01 is 2.02 AMU. 1 times 16 for oxygen is 16 AMU. Now you do add the masses to get the total mass of the water molecule, and that's 18.02 AMU. Now we're going to switch over to moles. We're going to multiply everything by 6.022 times 10 to the 23rd. So instead of 2 atoms of hydrogen, you have 2 moles of hydrogen. Instead of 1 atom of oxygen, you have 1 mole of oxygen atoms. That is 6.022 times 10 to the 23rd. And the water molecule, instead of having 1 water molecule, you have 1 mole, 1 times 6.022 times 10 to the 23rd water molecules. Okay. No matter what you defined a mole as, that could be true. You just switch from atoms, molecules to moles. Okay, that's fine. But the magic of the 6.022 times 10 to the 23rd number is in the molar mass. And it's, as we said several times, it's the same number, but it's in grams. So 2.02 grams, 16 grams, and then 18.02 grams. And as you start doing these calculations in the future, you're going to skip over the atoms, molecules, and atomic mass. We really don't work at that level. So we're working at the molar level, these big baskets of atoms and molecules that are big enough for us to see and big enough for us to weigh on a scale in the lab. So we're going to do a few calculations here. So how many grams is 3 moles of H2O? So here's what you do. Just look at the red box and look at the small red box inside. It says that 1 mole of H2O is going to require 1 mole of oxygen, 2 moles of hydrogen. 1 mole of H2O is going to require 2.02 grams of hydrogen. It's going to require 16 grams of oxygen, and it's going to be 18.02 grams, that 1 mole of water molecules. So in other words, you're just looking at the red box now to answer these questions. So how many grams is 3 moles of H2O? Well, if 1 mole of H2O is 18.02, then 3 moles is 3 times 18.02 grams. And that's going to give you 54.06 grams of H2O in 3 moles of H2O. That's the way I'd like you to write these answers. I'd like you to write it very completely so you're clear what you're saying here. It's not just numbers. How many moles of hydrogen are needed to make 4 moles of H2O? Well, look at inside the big red box. To make 1 mole of H2O, that's in the small box, it requires 2 moles of hydrogen. So to make 4 moles of H2O, you need 4 times 2 moles of hydrogen. So 4 times 2 is 8 moles of hydrogen are needed to make 4 moles of H2O. You're just scaling everything up to however many. If you wanted to make 1 cake and it required 2 cups of sugar, and then someone said, well, I want you to make 4 cakes. How many cups of sugar? Well, it's going to be 4 times 2 is 8 cups of sugar to make 4 cakes. That's all you're doing here. How many moles of oxygen are needed to make 3 moles of H2O? Well, you can see that you require 1 mole of oxygen for each mole of H2O you want to produce. So there are 3 times 1 equals 3 moles of oxygen are needed to make 3 moles of H2O. How many grams of oxygen are needed to make 3 moles of H2O? So to make 1 mole of H2O, you need 16 grams of oxygen. You see that in the big red box. So if you want 3 times that many moles of H2O, you need 3 times that many grams of oxygen. So there's 3 times 16, or 48 grams of oxygen to make 3 moles of H2O. Again, it's just like a recipe for a cake. Cups of sugar, flour, eggs. If you want to make twice as many cakes, you need twice as many of all those things. If you want to make 10 times as many cakes, you need 10 times as many of all of those things. And how many grams of hydrogen are needed to make 7 moles of H2O? So to make 1 mole of H2O, you need 2.02 grams of hydrogen. So to make 7 moles of H2O, you need 7 times that much. So 7 times 2.02 is 14.14 grams of hydrogen are needed to make 7 moles of H2O. So here's ways of writing molar mass. And you're going to come across these, and you want to be aware of how to use molar mass as a conversion factor, as equivalency, and as a conversion factor. So here's the molar mass for water, H2O. We already did that. So it's 18.02 grams for 1 mole of water. So first, there are several ways this can be written. First, you can write it as an equivalency. There's 1 mole H2O equals 18.02 grams of H2O. And I'm going to really be a stickler on this. I want you always to write the number, the unit of measure, and the substance. All three of those things. So 1 is the number, mole is the unit of measure, H2O is the substance. 18.02 is the number, grams, G is the unit of measure, and H2O is the substance. So there's an equivalency. You've seen that before. Now here's the one that you're going to often see in a problem. They're going to give it to you like this. The molar mass of H2O is 18.02 grams per mole. So you need to learn to convert that into the equivalency that you see above, or at least into the two conversion factors that you're going to see below. And there's the conversion factors. You've learned how to convert an equivalency into a conversion factor. You just put one of them over the other and then flip it, put the other one over the first one. So 18.02 grams H2O for every 1 mole of H2O, or there's 1 mole of H2O for every 18.02 grams of H2O. You're going to be using these conversions every single day in this class. So get comfortable with the equivalency. Get comfortable with seeing that shorthand method, because that's the way they'll often state it in a problem. The molar mass of H2O is 18.02 grams per mole. So you got to know how to deal with that. Okay. All right. Okay, so that takes care of this lesson on the mole. Again, why do we use a mole? We need a really big number of atoms or molecules so that we can actually see them and weigh them. Why do we use that specific big number, 6.02 times 10 to the 23rd? Because it takes the mass of a single atom or molecule or proton or whatever you're dealing with in atomic mass units and converts it to that exact same number in grams, which is something that we can work with. Or if we weigh something and we know what the substance is and we weigh it in grams, we can then work backwards and figure out how many atoms or molecules of that substance that we have. And that's really a miraculous thing, that we can know how many atoms or molecules that we're working with. But it's a very simple calculation to do that. Okay, so that takes care of this. Do the assignment, and we'll see you on the next lesson.